All right, so in the last part of our unit, the first section of it, what we did was we looked at motion in a straight line, which means the objects that we were talking about were always moving either north and south, east and west, left and right, forward, backwards. There was no angles involved, no two dimensions. All right, so that's what we're going to look at closer in this second part of this unit. And so what is going to be important is that we're going to have to deal with vectors quite a bit because, again, direction, if we're off a line, it's not going to be as easy as just making one direction positive and the other negative, because when we have off one line, we are going to have to use vectors more importantly. Now, again, just a little recap of what a scalar and a vector are. And those are the things we dealt with before, but this time, again, we're going to do it a little more extensive. So a scalar, again, is a quantity that is represented by its magnitude only. So you have something like 4 tests. Or let's see here, what else we got? Mass, where you've got 15 kilograms. What else? Time. We're looking at, say, 10 seconds. Those are all scalars. They're, again, all they're represented is by a number. Now, the most important thing for us is something like a vector, which is a quantity that was represented by magnitude, so a number, and direction. So, for example, if we're talking about a wind, well, we could have a wind, say, 20 kilometers an hour. And then directions here, we could have something like this, 20 degrees north of west. So that, again, is a vector because we have magnitude and direction. So now what we're going to look at is actually just drawing a vector. And so, for example, one, draw the wind vector 50 kilometers an hour, 30 degrees south of west. So what the heck does that mean and how do we draw it? Well, the first thing we got to be able to do is to draw what's called a compass rose. All right, and so it looks like a grid. So there we go, there's our grid. Now, you got to know where to put north, east, south, west. And so I have a little memory key that I use. And most of us know, I think, that north's at the top. But going clockwise, I use the memory key and a good word of advice, never enter stinky washrooms. There we go. So there's my compass rose. Never enter stinky washrooms. So I've got everything lined up in the proper axis. Now, what I want to do is draw this vector here, 50 kilometers an hour, 30 degrees south of west. Now, what this direction means is, first of all, south of west means we're going to be in the southwest quadrant, all right? Now, this means we're going to go 30 degrees towards the south from the west. So again, our vector is going to be in the southwest quadrant. So I'm just going to draw it in there. All right, now the key is, where's that angle? 30 degrees. Because when we're going to deal with vectors, next question, you have to draw the angle in properly. Otherwise, your answers will get messed up. So 30 degrees towards the south from the west. So that means we're starting from the west and we're moving towards the south. And so right in here would be my 30-degree angle. And again, I can label this vector as having a size of 50 kilometers per hour. So again, that is drawing the vector, putting the angle in the proper spot, and again, labeling our vector. All right, so that gets us to the next part.
I have a question quickly.
Sure, go ahead.
So like, what if it's not exact? Like, is that exact? Like, you just know off the top of your head that's 30 degrees? Or like, should we like?
Here's the thing is, I'm just labeling it.
Okay.
Is it exactly 30 degrees? Probably not. But what you're going to see in our next example of why I'm doing this is that we're going to find out exact measurements using trigonometry.
Okay.
Now, if we were in class, and you'll notice today that we are doing day 7 and 9. We're skipping day 8, which is graphically. And if we were in bricks and mortar school, we would be doing it graphically, where we'd be using a compass and ruler, Finding it out.
I
But because
see.
we're not, and I can't virtually do, or
Right,
can't
yeah.
do graphs, we're just going to go with algebraically.
Okay, sounds good. Thank you.
Okay, no problem. Good question. All right, so on that note, well, here's what we're going to look at for breaking apart vectors. Again, a lot of trigonometry today, so if you're good at trig, that's a good thing. If not, well, hopefully you learn it. Learn some to get better at it. All right, so on that note, what we're going to look at here is, I guess, B. We drew that vector. Oops, still wet. Don't want to wreck my markers. All right, so now we get to B. B part of that. We drew that vector, and I'll draw it again, but what I want to do is called determine the horizontal and vertical components of vector W, which was our wind vector, I said. I'm going to use the same one here, 50 kilometers an hour. And again, the direction was 30 degrees south of west. All right, so there we go. So that's the vector we were talking about. All right, so again, I'm going to draw it. All right, so I'm going to again draw my compass rose here. And again, never enter stinky washrooms. Again, there was our vector right here. 30-degree angle right in here, and it had a size of 50 kilometers an hour. All right, so again, I just redrew my vector. Now, something I did want to go through is that every vector can be written two different ways. And so this vector could also be vector W, which the size of the vector is not going to change. That wind is still 50 kilometers an hour. But in terms of my direction, I can rewrite it a little bit differently. And how I could rewrite it is that if this is a 30-degree angle in here, because our compass rose makes perfect 90-degree angles all the way around, that means the angle here could be 60 degrees right in here. Well, it is 60 degrees. And so another way to describe this vector is to say that it is 60 degrees, but instead of south of west, it would be west of south, which means 60 degrees towards the west, but from the south. So again, there's always two ways to describe a vector. Do I care which way you do it? No, it's always a pain for me when you write a quiz or something because there's two possible answers. All right, but again, the magnitude won't change. It's just talking about the direction that can change. So you have a perspective of either going from the west and moving towards the south, or starting at the south and moving towards the west. All right, so again, a couple ways to describe it. Now, here's what we're looking at now when I'm talking about the horizontal and vertical components. What we're looking at with the vertical components and vertical components is how much does that vector go up and how much does it go down or down. Vertical or horizontal components, we're looking at how much left the vector might go or how much right. In this case, it's going left and down, right? And again, that's the tricky part is you have to label your compass rose correctly. And so in this case, east and west are considered horizontal, north and south are considered vertical. So again, we want to look at how much up or down, that's the vertical component, and how much left or right our vector is going in terms of east and west. All right, so in this case, I look at my vector here, and what I've got here is a triangle. All right, so I'm going to kind of draw this out again, a little bit clearer, hopefully. So there's my vector, 30-degree angle right here. And again, it has a size of 50. All right. Now, let's go with horizontal first. Whoops, again, I better label my compass rose. Never enter stinky washrooms. All right. So the vertical component, horizontal component is again how much left or right. And so in this case, that purple line right there, that is what I would call W with a little V. Well, sorry, with a little H because we're doing horizontal here. And so that is what's called the horizontal component of vector W. I just picked W because it's a wind vector. All right, so there is our horizontal vector right there. Then how much up or down does this vector go? Well, it goes downwards. And so right here, this green line would be what's called our WV, the vertical component of our vector W. All right, now, what I've got here is a nice little triangle. That's why I said we're going to use some trigonometry today, quite a bit of trigonometry. And so if I look at finding my horizontal component, again, W with a little subscript H. All right, now, so I'll put a little dots here. I'm going to use trigonometry. I'm going to use the fact that my hypotenuse is 50. That's the length of the vector, and the vector is always going to be your hypotenuse. And because I'm finding this purple line, that's what we call my adjacent. And so what I'm going to look at is, again, using trigonometry, is that cos 30 degrees, because, again, I have my adjacent and I have my hypotenuse. Cozy at home, so my WH vector divided by 50, which is my hypotenuse. So again, just using trigonometry there. All right, I know it's the cos ratio because, again, I have my adjacent to the 30-degree angle and I've got my hypotenuse. Well, then I can, use trigonometry here. So what do we got here? Cos 30. Make sure your calculator's in degree mode. All right, I'm getting 0.87 equals WH over 50. All right, now I have a number equaling a fraction. So this is something I brought up many, many times, that when you have something equaling a fraction, the easiest thing to do is create a fraction equaling a fraction. Because now I can cross multiply. And so I have 1 times WH is WH. Then I have 0.87 times 50. All right, now WH, whatever 0.87 times 50 is, let's see here, 0.87 times 50 equals 43.5. Now, here's the key, because I'm not done yet, is the horizontal component of vector W is a vector itself, which means it has magnitude and direction. And that's why you'll see that I didn't put a little arrow sign on this WH until right here. Because this is unit-wise kilometers per hour, and I can look at my diagram and determine the direction. That purple arrow is headed left, which refers to west. There we go. And that is the horizontal component of vector W. Again, what I'm looking at is how much does my original vector move horizontally? It moves 43.5 kilometers an hour westward. Now we're going to do the same thing, but I'm going to get my vertical component. All right. So again, my WV is what I'm trying to find out. All right. Now, again, looking at trigonometry, I want to find the length of my green vector there. It is across from my 30-degree angle, which means it is the opposite side. Again, I have my hypotenuse here because that's the length of your vector. So if I have the opposite in the hypotenuse, I'm going to use the sine ratio. So I got sine 30 degrees is equal to my WV divided by my hypotenuse, which is 50. All right, so then I'm going to substitute back in, or do some figuring out here. So sine 30, let's see here, 0.5. All right, is equal to WV divided by 50. And again, I have something equaling a fraction where I like to create a fraction equaling a fraction, which I'll do again. There it is. And so, because that allows me to cross multiply, so I have 1 times WV is WV. All right, and then I have 0.5 times 50. Well, half of 50 is 25. But again, this vertical component of our vector W is a vector, and so I'm going to write it as such. And so I have my WV is equal to 25, let's put a little v there, 25 kilometers an hour. And again, because it's a vector, I need direction. And I look at, again, this is why I have my diagram here. The green arrow is pointing down, which refers to south. And so that is our direction. Now, a couple of things. Your horizontal and vertical components are always going to be straightforward directions. Your vertical is either going north or south. Your horizontal is either going east or west. And so when we found these horizontal and vertical components, again, what we're looking at is, here's our original vector. How much left or right does it go, or in this case, east and west? And how much north or south does it go? And again, in this case, south. And so that, again, is how we're going to break up our vectors into components, which is going to be very important, essential, I would say, for our next lesson, is then when we start to look at motion in 2 dimensions, we are going to have to start to put vectors together. And that is what we're going to look at our next lesson. Whoops.